Good morning, everyone. Welcome to this YouTube video series. So, in this video series, I want to introduce nanotechnology, and this course is very useful to BTech students, and also it is very useful to research scholars. So, who are new to nanotechnology and who are recently joined in material science. So, all this video lecture series is very helpful to all of you. I welcome you all to this video lecture series. So, I want to introduce myself. I'm Dr. Babu Batula. I'm currently working as a professor and dean, School of Sciences and Humanities, SR University, Warangal. So I have done my PhD in physics and I'm a material science scientist. I have 15 years of teaching and research experience. So I welcome you all to this video lecture series. So and these are my some of my research credentials. So the research publications and also related to projects information, and I have recognized as top 2% scientists in 2020 to 20, 2024, and also I have published many papers and I reviewed many papers, and I have awarded as Young Scientist Award in my PhD time. So these are my research credentials. So in this lecture series, so first I want to introduce nanotechnology, and it is a fundamental. In this lecture series, we are going to discuss fundamental concepts and also the practical applications related to the nanotechnology. So bridging fundamentals and applications in nanotechnology. So we are going to understand what is nanotechnology in these lecture series. Okay, so coming to the nanotechnology, so the basic thing is, so we are going to deal with the science at very small size. So that is nanoscale. What is a nanoscale? Nanoscale is nothing but it is a measurement. So here nanoscale means it is about 1 to 100 nanometers. So the whole thing related to nanotechnology lies here. You can see here why this tiny scale matters and how it's transforming fields like medicine, electronics, and energy. So that means, so when you make the objects into very small size, so the properties will change. So the same properties we observed at macro scale is very different when you bring the scale down. So that means when you minimize, when you decrease the size of objects, so then obviously automatically, so most of the properties will change. So in this lecture series or in this nanotechnology, so what happened when we scale down a material or to very tiny size? So that's what we are going to see in this video lecture series. Right. So introduction to nanoscale. So at this nanoscale. So we are going to explore the nanoscale, a tiny world. So why I am saying it is a tiny. So you can see here, you can see here. So this is measurements that we know very well. We are very familiar about this nanoscale. So this is the basic measurement, that is meter. Meter. This is the very fundamental measurement. So if you go up, so you can see kilometer, megameter, gigameter, terameter, petameter, hexameter. So that means 10 power 3 meters, 10 power 6 meters, 10 power 9 meters, 10 power 12 meters, 10 power 15 meters, 10 power 18 meters. In the similar way, if you go down, you can find millimeter, 10 power minus 3 meters, micrometer, 10 power minus 6 meters, nanometer, 10 to the power minus 9 meters, picometer, femtometer, attometer. So as per our subject, so ours is related to here. So 10 to the power minus 9 meters. So that is nanometer. So we are going to deal objects, or we are going to study the science at this scale. So we are going to study the science at this small size. That means at 10 to the power minus 9 meters. So what is happening? How the properties will change? How the material will behave? So we are going to study the science at 10 to the power minus 9 meters. That is a nanometer, right? So here this side, if you see here, so you can see the sizes of different objects or different things. You can see the human size, so it is in order of 10 power 0. You can see here, these are all macro objects. If you go down, eraser and a hair, so blood cells, virus, bacteria, DNA, and this is some nanomaterial morphology and water molecules. That means from top to bottom, you can see the size reduction. You can see the size reduction. How from top to bottom, you can see the small size, the human size from eraser, from hair. So you can see the size reduction in these objects. Okay, so so that means from macro scale to it is going to micro, and then it is going to nano, and it is going to picometer level. Okay, so this is the size reduction in terms of measurement for our understanding. Next, yes. Now, how can we define nanoscale? How can we define nanoscale? What is the nanoscale? What is the nanomaterial? What is the nanotechnology? So we need to understand what is the definition of nanoscale. Nanoscale refers to structures with dimensions between 1 and 100 nanometers. What is the meaning? What is the meaning? So, for example, if you take a mobile phone, so you cannot say this is in nanoscale, okay? Because so how can we say a material is in nanometers, or how can we say it is in nano scale? That means so for every object, it has some length, breadth, height, right? So three dimensions. So one in any one of the dimensions, whether in length or width or height, any one of the dimension should fall under 100 nanometers. So whenever any one of these dimensions is below this 100 nanometers, then we can say that it is a nanomaterial. Whether it is a length or breadth or height, any one of these must be within 100 nanometers, within 100 nanometers. Then we can say that it is a nanomaterial, or we can say this material can fall in the range of nanoscale. Okay, right. So nanoscale refers to structures with dimensions between 1 and 100 nanometers. So, and also we can define this like this. A nanometer is 1 billionth of a meter. So 10 to the power minus 9 meters. So whenever you are writing 1 nanometer is equal to 1 nanometer is equal to how much? 10 to the power minus 9 meters. So what is the beauty of this technology, or what is the major significant change at the nanoscale? So that is, at this scale, materials exhibit unique physical and chemical properties. That means, so there is an abrupt change, there is a significant change of the same material at macro size, the same material at nano size behaves differently. The same object at different sizes behave differently. So that is the significance of nanoscale. And also why it behaves like that. The major difference is at this nanoscale, quantum mechanical effects become significant. And also in coming slides or in next classes, next lectures, we can see quantum confinement effect. So this quantum confinement effect is one of the major reason for the different behavior of the material at nano scale. Okay, understanding the nanoscale is crucial for advancing nanotechnology. So, if you want to do anything at any applications related to nanotechnology, first thing you need to understand the nanoscale behavior. So how these materials at nanoscale behave differently. So once you know the science or the reasons behind this material, so that you can utilize for different applications related to nanotechnology, right? What is the nanoscale? So we will dig deeper, or we will understand more about this nano scale. Okay, right. If you see this picture here, you can see, so in the previous slides we see top top to down. So we observed the size reduction, the size reduction. Similarly, here also you can observe, so from left to right, size increasing, or from right to left, you can see the size reduction. So watermelon, so its diameter around, it's, it's not exactly, it's a rough estimation, it's around 15 centimeters, right? 15 centimeters. So, and also if you take a coin, if you take a coin, so it is 2 centimeter. And also a dot, it is in 1 millimeter. Then human hair, red blood size, red blood cell size, it is around 5 micrometers. If you take a virus, it is it is in the range of 1 micrometer, that is 10 to the power minus 6 meters. And also you can see this is a carbon nanotube, its diameter is around 5 nanometers. Then gold nanoparticles, and then graphene sheet, then water molecule. So you can imagine the size, you can imagine the size of the these objects. So if you see, the hair size is around 100 micrometers, 100 micrometers. Red blood cell, 5 micrometers. You can see the significant reduction in the size range, in the size range. Okay, okay, we will see the major explanation about this figure. You can see size spectrum visualization. The image illustrates the scale of objects from atomic dimensions to macroscopic items, 15 centimeter, offering a comparative perspective. So this is atomic level size. This is atomic level size. This is macro level size. So from atomic level size to macro level size, you can see the different size ranges in this figure. Okay, so where is the nanomaterial? Nanomaterial means 1 nanometer is equal to 10 to the power minus 9 meters, right? 10 to the power minus 9 meters. So and also, where how can we define nanoscale? So one of the dimension should be within 1 to 100 nanometers, 1 to 100 nanometers. So out of these materials, so which comes under nanomaterial range? You can see graphene sheet 1 nanometer, carbon nanotube 5 nanometer, gold nanoparticles 10 nanometers. So these fall under nanometer. That's why you can see here nanomaterials. Okay, nano. This is atomic level. If you take a water molecule, so this is 0.1 nanometer. So this is atomic level. Then nanomaterial size, this is micro size, this is micro size, and this is macro size. Okay, macro size. So that's why you can see here carbon materials, graphene sheet, carbon nanotubes, gold nanoparticles, these are all fall under nanomaterials range, nanomaterials range. And also biological comparison. See, the biological comparison means this is virus, red blood cells, this is micro size, micro size. You can see biological entities like viruses 1 micrometer, and also red blood cells 5 micrometers are significantly larger than nanomaterial. So these micro size, this virus and the red blood cells, these are larger than nanomaterials, larger than nanomaterials. And also in everyday objects we can see our hair is in the range of 100 micrometers. So by comparing this nanoparticle with your hair size, you can see how many times it is lesser, less thickness than our hair. It is in the order of 100 micrometers, 100 micrometers, but it is 10 nanometers, right? 10 nanometers. So yeah, coming to the importance of scale in nanoscience, understanding the size regime is crucial as materials at the nanoscale demonstrate quantum effects and enhanced surface area essential for applications in catalysis, sensors, and energy storage. So, if you want to understand different applications, so you need to understand the science at nano level. You need to understand how to prepare nanomaterials, what are the properties of nanomaterials, what are the requirement of nanomaterials. For for different applications, we need different materials. We need different nanomaterials. So based on the application, you need to design different nanomaterials. If you need to design nanomaterials, you need to understand the basic things that is about nanoscale. So from these two slides, I think you got the knowledge or you are aware of this. What is the difference between macro size, micro size, and nano size? Okay, nano size. So these two things, watermelon, coins, a dot. These are all macro size. And hair, red blood cell, virus in micro size. Coming to nanomaterials, graphene sheet, carbon nanotube, gold nanoparticle. These are all under nanomaterial. So this is water molecule. It is comes under atomic level. So from atomic level, nano size, micro size, macro size. Okay, so this is about nano scale. So you need to understand how small is the nano size. You need to understand how small, how tiny is the nano scale range. Okay, we cannot see with our naked eyes. Okay, we should use microscopes. Okay, microscopes. And we need, if we want to see the nanomaterials, we need even advanced devices with not microscopes. We need there is electron microscopes. So to observe nanomaterials, we need electron microscopes. Next slide. Yeah. So these are some of the nano structures. Some of nano structures. I already told you, nano means it should be in the order of 10 to the power minus 9 meters. So that is 1 nanometer. So if you see this one, if you see this, these are nanoparticles. Okay, so if you see here, nanoparticles. And also you can observe here, it is in the, this size is 200 nanometer. So this is 200 nanometers. So don't confuse that. I already told you that nanomaterial means it is under 100 nanometers. So this scale is 200 nanometers. So if you observe the diameter of this particle, so it should be less than 100 nanometers. That's why we can call it as a nanomaterials. So these morphology, so this is nanoparticles. These are nanotubes. Nanotubes. So these are nanotubes, and these are nanoflowers. Nanoflowers, and also you can see these are all nanosheets. Okay, so just like our rose flower pebbles. Okay, so it's very thin. So the thickness of this pebble or this sheet is definitely under 100 nanometer. So these are all nano flowers. And you can see these are all nano cubes. Okay, these are all nano cubes. This is a special this is a structure. We can call it as tetrapods. Okay, tetrapods. These are all nano structures. We can have thousands different morphologies, different shapes in nanostructures. So there is a lot of varieties in nanostructures, and every nanostructure is very unique in terms of its properties. Okay, every nanostructure has its own different properties and also applications. Okay, so just to understand how the nanomaterials looks like, it has different morphologies. For your understanding, I am showing some of the basic morphologies: nanoparticles, nanotubes, nanoflowers, nanocubes, and these nanotetrapods. Okay, right. So what is the significance of the nanoscale in nanotechnology? So usually everyone listen to nanotechnology. We usually heard about nanotechnology in different applications in different fields. But what is the significance of nanoscale in nanotechnology? Right. At the nanoscale, if you see the first point, at the nanoscale, materials can exhibit enhanced strength, lighter weight, and increased chemical reactivity. What does it mean? For example, if you take if you take a car in our maybe in uh, 10 years back, 15 years back, 20 years back, Ambassador car is very famous in India. Okay, it is very strong. It is very strong. It is the symbol the of most politicians, government servants used Ambassador car. But if you see the weight of the car, it is very heavy because of its materials that used to make the Ambassador car. Okay, so but if you want more efficient car, that means more mileage, so that means the car weight should be less, the car weight should be less, and also it should provide the same safety, the same safety. So that means we need to make some other materials which lighter and also provide high safety in case in cases of in case of accidents. Okay, so that means so we are changing the materials. So when you change the materials, so we need to find new materials which should provide lighter weight and also safety. In same way, if you think of aeroplanes, so aeroplanes also should be lighter weight, should be lighter weight. Otherwise, if it is more weight, so it consumes more fuel, so less mileage. So there is a lot of drawbacks. Okay, lot of problems with heavy weight. So that means so we need to make materials such a way that it should provide strength, less weight, right? So how can that means so we are nowadays we are using carbon materials, carbon nanotubes, graphene. So these materials are very less in weight, very lightweight, yet it provides high strength, high strength. So this is the beauty of nanomaterials or nanotechnology. Okay, so what is happening here? The same material, the same iron or the same steel. So if you make it down to nanoscale, so nanomaterial, nano iron, so what is happening? So it is producing or it provides different properties, lighter weight and also enhanced strength. Okay, so likewise some other applications: unique optical properties such as quantum dots emitting specific wavelength of lights. So similarly, not only the physical strength, but in optical properties also we can see significant changes. For example, if you see the display technology, so nowadays we are using quantum dot LEDs. Okay, very advanced display technologies. So previously we used very old techniques. So the televisions looks heavy, not that much bright, not that much colors. So nowadays we are using very bright displays at very lightweight. So in coming days, we can see the flexible display devices. Okay, nowadays we are also seeing the foldable phones. Okay, so that means so how all these technologies became reality, that is because of this nanotechnology, and at this because of this nanotechnology and this nanomaterials, because of the provision or of this interesting properties, we are all these became reality in today's life. Okay, so and also increased surface area to volume ratio enhances catalytic activity, any activity. So one of the strong reasons for the for this nanotechnology, so what is the one of the major reason, one of the major reason is the increased surface area to volume ratio. So what does it mean? I will explain in coming classes also. Okay, so this is the one of the major reason for the for showing different properties of same material at nanoscale, increased surface area to volume ratio. And also quantum effects can alter electrical and magnetic properties, and also enables develop of innovative applications across various industries. Okay, so to play nanotechnology in a big role in today's advancements, these are the main reasons. Okay, what is the main reasons? At nano scale, the same materials, so we are not prepared very new elements, we are doing the same experiments, or we are making the same materials, same iron, we are using same elements whatever available in our periodic table, but we are making materials at very tiny size, nano size. So because of this nano size, the same materials exhibit different properties. Okay, different properties, and these different properties makes nanomaterials very useful in nanotechnology applications. What are the main reasons? What are the main reasons? This one, increased surface area to volume ratio, and also quantum effects. These two are the main reasons for this nano science. Okay, nano science. Okay, we'll go further. Yeah, so size dependent properties. So we are saying that at nano level properties will change. So what kind of properties will change? What it matters? If the properties will change, how it affects the end application. For example, electrical properties, mechanical properties, okay, chemical properties, magnetic properties, how it will change. Okay, let's see some of the major changes due to size. Okay, some of the major changes due to size. So coming to uh, initially, see this one, nanomaterials can exhibit different colors due to quantum size effects. So I already told you in previous slide also. See this one, quantum effects can alter electrical and magnetic properties. Okay, so that because of this quantum size, because of this small nano size, so it exhibit different colors. For example, if you see, if you take gold, gold, so when you gold is in yellow color, right? Gold is in yellow color. Okay, so when you take if you see a ring or chain, bracelet, whatever, you can, all the gold ornaments looks in yellow color. But the same gold at nano size is not in yellow color, is not in yellow color. Okay, it is in some other color. I will explain, I'll show it later. Okay, right? So that means nanomaterials can exhibit different colors due to quantum size effects. Okay, right. And next one, mechanical properties. such as hardness and elasticity can be enhanced. Okay, so mechanical properties, toughness, hardness, or elasticity can be enhanced. For example, what is the advantage of enhancing this hardness? Okay, so for example, if you take any material, so it is very flexible but very strong. For example, if you see our touch screens, okay, touch screens should be very sensitive, it should be very responsive, and also it should be durable. It should be durable. For example, if one's phone fall down, if the display immediately broken, so that's not a good display, right? That's not a good display. So we need to make a material, even such cases, even mobile fall down, it should not be broken, the display should not be broken. So that means it should sustain, or it should retain that force. That means, so how can we make these material, how can we make displays with such properties? By using nanomaterials, by using nanotechnology. So by modifying the properties, we can change. If you make material with nanomaterials, so it can provide toughness, it can provide flexibility, it can provide hardness, right? So whatever the enhanced requirements we need, so we can achieve by using nanomaterials. Okay, we can achieve by using nanomaterials. Okay, so coming to electrical conductivity. So electrical conductivity may increase or decrease depending on the material. So if you use nanomaterial, you can enhance the electrical properties. For example, if you take this one, this is nanotubes, okay, nanotubes, and also you can see carbon nanotubes. By using this graphene sheets, carbon nanotubes, you can enhance the electrical conductivity. Once the electrical conductivity enhance means, we can we can use it for many applications, right? Because their resistivity is less, resistance will decrease, so automatically conductivity will enhance. Okay, so to achieve higher electrical conductivity, we can use these nanomaterials. Okay, these nanomaterials. And also you can, coming to magnetic properties, magnetic properties can change, leading to super paramagnetism. So nowadays we are using magnetic levitation in Japan and maybe China. Japan uses using magnetic levitation train, so it is because of superconductivity. So for these advanced technologies, so we can use different magnetic materials, which provides different new applications like super paramagnetism, superconductivity, etc. Okay, so what I want to what I want to inform you is, so due to nanomaterials, the new properties will evolve, new technologies, new applications we can achieve. Okay, for example, if you see the chemical, this point, chemical reactivity often increases, affecting stability and catalytic activity. Okay, catalytic activity. So most of the prop- properties, many of the properties, be it mechanical properties, electrical properties, magnetic properties, chemical properties. So all these properties will change. All these properties will change. So these properties at macro level is different. The same magnetic, optical, electrical properties at micro size is different. The same mechanical, electrical, magnetic, chemical properties at nano level is very different. Is very different. So at nano level, so we can achieve these properties for better applications, for better applications. Okay, so we can find these materials, these nanomaterials, with these properties, we can utilize it for different applications of today's world. So in coming slides, we can see how these properties will change in our daily life. Okay, so we will see it, right? Why we need to study the nanoscale? Why we need to study the nanoscale? Why we need to study nanomaterials? Why we need to prepare nanomaterials? Why we need to study nanotechnology? By seeing this slide, you can understand how important, how essential we need to study this nano science or nanotechnology. Okay, right. We will see. See here, I provided some of the images, so you can see. So I will just enhance this image. See this one. So what is this image? What is this image? This is nanoparticles. These are nanoparticles. Where we are using this one? In drug delivery. In drug delivery. So we will take medicine, right? So whenever we have sickness, we will use medicine, right? So this is a nanomaterial. You see this one? This is the medicine. This is the medicine. So and this is a nanomaterial. You can think like a graphene sheet or carbon nanotube like structure. So it will use in drug delivery system. Okay, right. Okay, we will understand one by one. So why we need to study nanoscale? See this one, unique properties at nanoscale. We already discussed. Materials at nanoscale exhibit quantum effects and increased surface to volume ratio. And also at nanoscale, it provides novel electronic, optical, and magnetic behaviors not observed in bulk counterparts. So this is what I am telling from the starting of this lecture, that the properties at bulk stage, that means at macro size, the properties are different. At nanoscale, the properties are very different. What are the reasons for the different properties at nanoscale? Quantum effects and also surface to volume ratio. These are the main reasons for showing different properties at nanoscale. Okay, right. Second one, advanced material design. See, nanostructures like fluorines and carbon nanotubes offer unprecedented strength, conductivity, flexibility, enabling breakthroughs in material science and nano engineering. It is a fullerene, it's a carbon structure. Okay, carbon structure. So these can be utilized to carry the medicine to a proper place. So if you take a medicine, it will flow, it will dissolve in blood, it will it will it will it will travel our whole body. But if we want to take the medicine to the affected area, only to that particular area, so we need this efficient drug delivery system. So these nanomaterials can take the medicine to exactly the affected area or where you want to deposit that material. These nanobots, nanorobots or nanobots are useful to carry the drug to a specified place. Okay, so in this way it is very useful. Okay, right. So and the next application, revolutionizing technology. Quantum dots enhance display technologies, quantum dot display, by offering high brightness, energy efficiency, and vivid color resolution. For example, if you see this one, you see this one. So this is quantum dot display. Nowadays, I think Samsung and LG brands providing these quantum dot displays. If you see the quantum dot display, it is very bright. It is very bright. It gives most efficient color display. Okay, so this is the advantage, this is the advantage of the nano scale. So it saves energy, it consumes very less energy, it provides very bright and clear images, video display videos. Okay, so and it is energy efficient. So what else we need? For a television should be very bright, energy efficient, right? So nanotechnology is playing a big role in display technology. Okay, so this is a carbon nanotube. So these carbon nanotubes are useful in this, right? And also other applications you can see. If you see this image, if you see this image, see how different, how many different applications we have by using nanotechnology. You can see here optical engineering, defense and security. Okay, so in defense, in rockets, in satellites, where all it is by nanotechnology. Mostly, mostly. For example, if you want to use rocket, if it is very heavy, it is very tough to launch. We need lightweight, right? We need lightweight, and also it should be very strong. It should be strong because it should, whenever it enters into the air atmosphere from space, right? So there is so much drag, so much force. It should sustain, right? So and also in space technologies, right? So in defense, in space, so nanotechnology is very very essential, very crucial. And also in bioengineering, so in making many devices, for example diagnosis, like MRI, CT scans, right? um, Something like diagnosis, what is it called? So in many medical devices, we are using this nanotechnology, and also in cosmetics. So, for example, if you observe cricketers, so what they will do? So, whenever they are playing in sunny day, so they used to cover with some cream, right? Why they are using that cream? So it will absorb UV rays, or it will reflect UV rays, so that their skin may not damage. And also nano fabrics, okay, in textile industry, in chemistry, in energy, in batteries, okay, in electrical vehicles, and also in medicine, in nano devices. So wherever you take any application you take in this world, there is nanotechnology. There is nanotechnology. So it is very, very essential to understand this nanotechnology. Okay, so this is very, very essential for all the students to understand this highly advanced technology, that is nanotechnology. Okay, and also it is not related to a single field, it is not related to a particular single application, it is a multidisciplinary. Okay, it is interdisciplinary subject. Okay, so the study of the nanoscale fosters innovation at interface of physics, chemistry, biology, and engineering, paving the way for next generation devices and sustainable applications. So it is a very very diverse subject. It is there in every subjects, in every science, in physics, in chemistry, in biology, in engineering, in electronics, in mechanics, in civil. So it is there, its applications, nanotechnology applications are there in every field, in every engineering stream, right? So that's why it is essential for every student to understand this nanotechnology. Okay, this nanotechnology, right? Okay, so everything has some history, right? So likewise, nanotechnology also has a history of many decades. Okay, so who is the father of nanotechnology? Who laid a foundation to nanotechnology? So he's the famous physicist. He's a famous physicist, and his name is Richard Feynman. Okay, Richard Feynman. So in his 19, he gave a quotation. It's a very famous related to nanotechnology. That is, there is plenty of room at the bottom. Think of it. What is the meaning of this statement? There is a plenty of room at the bottom. What is it meaning? In general, in general, if you see any surface or floor of the room, so if you see a floor of the room, you can see just bottom. So our vision will stop at the bottom, at the surface. But if you see, so whatever we are seeing with our naked eye, so that is at macro level. That is at macro level only. Okay, but there is so much to see. Maybe we cannot see our naked eyes. That doesn't mean there is that is that's only there, right? So there is something beyond our vision capacity. So there is so much to see. There is so much to see. There is plenty of room at the bottom. So that means, if you, for example, if you see a blood, if you see a blood, for example, if something happened to our skin, we can see that there is blood. But can we see the blood cells? No, we cannot see the blood cells through our vision, through our naked eyes. But you can, if you use microscope, you can see something more. You can see something more through microscopes. If you use electron microscopes, even you can see the nano size. So that means the meaning of this statement, there is plenty of room at the bottom. That means his idea or his statement is, there is so much to see, there is so much to explore beyond our vision capabilities. There is so much. So that is the very famous statement given by Richard Feynman in 1959. There is plenty of room at the bottom. Conceptual foundation for he laid the conceptual foundation for nanotechnology. Okay, so if you see this picture, so this is the STM. So that means scanning tunneling microscopes. These are the very first device to see the objects beyond our vision capabilities. Okay, so this was invented in 1981, enabled atomic scale manipulation. Atomic scale manipulation. Manipulation means it's nothing but say fabrication. Okay, it's a fabrication of material at atomic level. Okay, and also, so discovery of fullerenes, for example C20, we can call it as a buckyball. Okay, so these are all carbon allotropes, we can call it as fullerenes. We can call it as fullerenes. Okay, carbon materials. So discovery of fullerenes revolutionized carbon nanostructures. Okay, I already shown you carbon nanostructure means graphene, single layer carbon nanotubes, single walled carbon nanotubes, multi walled carbon nanotubes. So these are all breakthroughs in nanotechnology. Early breakthroughs paved the way for nanoscience and nano engineering. So this is the he is the pillar or foundation. His ideas are the foundation to evolve this nanotechnology. Okay, so regarding nanotechnology, so we need to we must know him. So his name is Richard Feynman. He's a physicist. Okay, he's a physics scientist basically, right? So coming to our core subject, coming to our core concept, what is nanoscale, what is macro scale, what is macro scale. So in initial, if you see, yeah, this one, this slide, you can see this is macro scale, micro scale, nanoscale, and this is atomic scale. Atomic scale. So our focus is nanomaterials, right? Our focus is nanomaterial. Our focus is nanomaterial. Okay, So then how can we distinguish this nanomaterial? This is macro, macro, micro, nano, right? Macro, micro, nano, right? So if you see here, so this is nanoscale versus macro scale. See this object, if you see this object, this is macro object. Okay, this is macro object. So for example, just let us assume this is a cube, right? So one side, every side of this cube is 1 meter. Okay, so the surface area is 6 meter square. Okay, the surface area is 6 meter square, right? So the same cube is divided into 8 cubes. Okay, is divided into 8 cubes. Okay, 8 cubes. Then what is happening? So the side of this piece, the side of this piece became 0.5. Initially it is 1 meter, right? Initially it is 1 meter. So then it became 0.5 meter, 0.5 meter, 0.5 meter. So what happened here? The surface area will, of all these bricks will become 12 meter square. Okay, surface area of this cube is, the surface area of all cubes became 12 meter square. And also if you further divide into these cubes, which has which individual side became 0.25 meter, then what about the surface of the total cubes? 24 meter square. Are we added anything? No, we taken the initial cube, we taken initial cube, and the surface area is 6 meter square. We cut it down to 8 cubes, the same cube into 8 cubes, the surface area is 12 meter square. The same cube into these many pieces, the surface area will become 24 meter square. What is happening? Why the surface area increases here? The same, the same object. See, reducing particle size increases total surface area dramatically. What is happening is, here this is the only surface, so 6 sides, so this surface area only exposing. Okay, this is the only surface area is exposing. Okay, if you cut it down into pieces, what is happening? So we are creating the surface to expose new faces. Okay, new faces come into picture to expose. And also here also, so that means, so whenever you make down the material into several parts, so that means more surface area, more area coming to picture to expose its surface. Okay, so that's why the surface will expose. For example, for example, see this one. So this is a handkerchief. Okay, so I folded like this. Okay, I folded, right? So this is the, so how much surface area it has to expose? So very limited surface area. Okay, very limited surface area. But if you open this, what is happening? Its surface area is increasing. See how much surface area? So this is one surface area, another surface area, right? So if you open, so this is, right? See, so much surface area. Okay, so much surface area. That means, so like this, like this, so you can see, like this you can see, so much surface area will expose. So by observing this picture, you can understand that reducing particle size increases total surface area dramatically. And also higher surface area enhances reactivity and functional properties. Okay, so there is two ways to make a nanomaterial. Okay, so that is, one is top down approach. That means we will take a macro object and we make it down to nanoscale. Okay, we make it down to nanoscale. So that is one approach, and second approach is bottom-up approach. So that means we will we will manipulate at atomic level so that we can make a nano particle nanomaterials. Okay, bottom up approach. So there are two ways to make nanomaterials. So that is top-down approach and bottom-up approach. In top-down approach, so bulk material broken down via grinding or milling. Okay, so if you see here, you this is a bulk, this is a macro size, right? So if you broke down into many pieces, again many pieces, again, so that means, so the size is step by step reducing so that it come to nano size. So when a particle, one of its dimension comes down within 100 nanometers, so then it is a nanomaterial. So this is top down approach. Okay, but if you take atoms atomic level, if you make atomic level by using some chemical processes, chemical synthesis processes, so that we can make it into bottom up. Okay, bottom up approach. So this is bottom up. We will know in detail further. Okay, so this is a top down approach and this is bottom up approach, two approaches. Okay, right. So yeah, we can see here also the nanoscale versus macro scale. If you see macro size, micro size and nano size, we already seen the same information through some other picture previously. Okay, so objects like humans, apples, ants, so these are all comes under macro size, and this is micro and nano. And yeah, so macro size, micro size, nanoscale, and size affects properties. Okay, so if you see this one, so this figure is very interesting. This figure is very interesting. See this one. See, I told you right previously. So it's a nanoparticles. Okay, nanoparticles, and this is the colors, right? Colors. So at nanoscale level, every small change in its size is very significant. For example, if you see these two bottles, so this is, that means here the particles in 80 nanometers, here the particle is 90 nanometers. See, in this range, the particle size difference, so it makes different colors. Okay, different colors. Okay, so that's why I told you earlier that if you take a gold particle, so it has different, so this color will be very different for the same material in macro size and micro size. See here, for every change, so this is the absorption. So the absorption will change. Absorption change means automatically color will change. Okay, color will change. Right. So size affect properties. See the optical color change of gold particles from 30 to 90 nanometers demonstrates size dependent behavior at the nanoscale. See the color of gold particles. So usually when we see gold ornaments, so it is in yellow color, but the same gold, but it is nano gold. Okay, nano gold. So gold particles at nano size, in the nano range, the color is, see the pink, something like red, wine red color. This is purple color. Okay, the color is very different. The color is very different for optical this gold nanoparticles in nano size. Okay, so transitioning from macro to nano enables new phenomena, optical, electrical and biological, that are the key to nanotechnology and materials science. So I told you earlier, we have seen how the properties will change the application. Okay, the change the application, all the applications, most of the properties, mechanical properties, electrical properties. So all these properties will change at nanoscale when it comes down from macro size. Okay, macro size. Yeah, see, this is very interesting. Importance in nature, biomimicry. What is biomimicry? That means resembling in nature. Okay, for example, if you see, so this is a TEM image. So it is TEM means this is an electron microscope. Okay, this is an electron microscope. So this is SEM, scanning electron microscope, tunneling electron microscopes. So that means we can see through these devices, we can see the nano size particles. Okay, nano size, we can see the nano size particles. Okay, you can see the nano size particles. So you can see, so it's something like lizard. So if you see the surface of its skin, you can see the pore size structures, pore size structures. So that means we can see nanotechnology in nature also. We can see nanotechnology in nature. Okay, where do we can see this? For example, this lizard type animals, they can easily stick to the surface to climb the walls. Okay, to climb the walls. So it's a nanotechnology. So it's nothing but a nanotechnology which we can find in nature. And also you can see the lotus flower, lotus leaf. So this water float on this lotus leaf. So it cannot wet. Okay, it cannot be wet. It just flow, flows. It passes on leaf, so it cannot make it wet. Okay, so this is nothing but it's a nanotechnology. So if you see the surface, if you see the surface of this lotus leaf, so you can see like this. Okay, you can see like this. So nature as a nanotech engineer. So that means I already told you, we can see the implications or the properties of nanotechnology. So what we observed in nanomaterials, we can observe in nature also. Okay, so many natural surfaces exhibit unique nano and microstructures, offering inspiration for advanced materials. Right. So here we can see the nanotechnology. So in this surface, here this surface also. Nowadays we are making self-cleaning surfaces, right? Self-cleaning. For example, if you if you coat some glass surface with nanotechnology, so it will automatically clean. The dust particles cannot stay on the glass surface, it will fall down immediately, right? So that is a kind of nanotechnology. So this nanotechnology, it is there already on the surface of lotus lotus leaves. So we can inspire many things, many applications, or many properties from the nature. That's what I wrote here. Many natural surfaces exhibit unique nano microstructures, offering inspiration for advanced materials. Okay, so see the some images reveal hierarchical structures that enables to climb vertical surfaces. Okay, see this one. So this is what these hierarchical structures are very helpful. See our hand. So we don't have that kind of structure, right? We don't have that kind of structure. So that's why we cannot climb. But if you see the Spider-Man movie, so his hands structure will different, right? So he finds some needle like structures. So that's what here, what it has. So because of this surface, this animal can climb the surface. Okay, and also lotus leaf, it is super hydrophobicity. So we usually surfaces usually hydrophobic or hydrophilic. Okay, so this lotus leaf is super hydrophobicity. If it is hydrophobic, so the objects will slide down, so it cannot stay on the surface. It cannot surface. See this one. Some images show nanostructured structure, okay, that repel water. So it is inspiring for self-cleaning and waterproof materials. For example, raincoat. Okay, so we are wearing raincoats. So when on a rainy day we wear a raincoat. So whatever the rain falls on the raincoat, it will slide down. It will slide down. So that our shirts cannot wet. Okay, it cannot wet. So that means some surfaces we are making now these raincoats, but the nature already created in lotus leaf surface, hydrophobic surface. Okay, hydrophobic surfaces, right? And virus particles. See, yeah, these are the virus particles. So we can see by using electron microscopes only. Even we cannot see through microscopes. We need the powerful electron microscopes to see these this much small virus particles. Okay, nature inspired design. See, biological surfaces motivate the development of smart materials for water harvesting, energy devices, and surface coatings. So this slides gives the information that already nanotechnology is there in nature. So we need to find. See, we can inspire the aviation technology from birds, how the birds are flying, how the wings, which by studying the bird wings or the shape of the wings, we inspired to make aeroplanes. Likewise, coming in case of nanotechnology also, we can inspire from the nature to make different materials for different applications. Okay, for different applications. So that's why, so we need to, this is the biomimicry in nature. Okay, so we need to learn many things. So that's why observation is very important. So observation is, observing nature is very different. So by observing the nature and the applications or the advantages, we can inspire many things. Okay, to make things, to make devices, to make new devices. Okay, for our daily life. So observing nature is very important. So that's what, from nanotechnology perspective also, there is nanotechnology in nature. So our job is to find where it is. Okay, coming to tools for nanoscale exploration. See, to study nanoscale objects, nanoscale materials or nanomaterials, so we need many new techniques. Okay, to study. To prepare, we need new methods. To observe, we need new techniques. And also to analyze its performance, we need new devices. Okay, so because it is a new technology, of course it is there from last 30 years. Okay, but we need new separate devices. We need new techniques to study, to observe, to study, to characterize, right? To to study the properties, okay? To study the properties or to perform any tests. So we need new techniques, right? New techniques. So these are the tools for nanoscale exploration. So we need all of these and so many more devices. Okay, so these are all some methods and techniques, right? We need optical microscopes, we need electron microscopes. In electron microscopes we need scanning electron microscope, transmission electron microscope, scanning probe microscopes. Okay, so AFM, atomic force microscopes. And also we need X-ray analysis, EDS, WDS, XRD. So and FIB, and these are all FTIR, AES, XPS, XRF, Raman spectroscopy. Raman spectroscopy. These are all the techniques which are essential, which are crucial. We must have these devices to see nanomaterials, to observe nanomaterials, to study its properties, whether it is optical properties, electrical properties, okay, vibrational properties, optical properties. So, and how the with which what kind of materials this material prepared. Okay, so we need all these devices and techniques or methods for the to achieve or to study the nanoscale materials. Okay, nanoscale materials. So these are all essential: electron microscopes, optical microscopes, so XRD, X-ray analysis. So these are all essential. Okay, so these are all essential devices, essential tools. Okay, essential tools. Right. So coming to nanoscale fabrication, we already discussed a little earlier that how can we make nanoscale materials. In two ways we can make nanoscale materials. In two ways we can make nanoscale materials. So what are that? One is top down approach, second one is bottom up approach. Okay, first one is top down approach. Top down approach means we will take bulk material, we are make it down, so we cut it down again and again and again, so that it will come to nano size, nanoparticle size. Okay, that is top down approach. That means we take bulk material and we make it down to nano size. So that is top down approach. Top down approach. So what are the top down approach methods? Some of, see here, this is bulk, this is bulk. So by using top down we make it into nanoparticles. Okay, nanoparticle. This is top down approach. So what are the examples for top down approach? One of them is sputtering, chemical etching, thermal ablation or laser ablation, mechanical process, that is ball milling, and by explosion process. Okay, so these are the examples for top down approach. Okay, top down approach, top down approach. And the second approach is bottom up approach. Second approach is bottom up approach. So in bottom up approach, what we'll do, we will manipulate the atoms, we will manipulate the atoms, we will manipulate the atoms, and we make it into clusters and then to nanoparticles. Okay, so atomic level to nano level, atomic level to nano level. That is bottom up approach. Okay, bottom up approach. So what are the examples for bottom up approach? See here, atoms, we are taking atoms and we make it into nanoparticles. Okay, so some of the examples for bottom up approach is bioreduction, aerosol processes, electrochemical deposition, spray pyrolysis, sol gel, vapor deposition, and atomic or molecular condensation. So these are the methods or processes or techniques for bottom up approach. Okay, so usually we make nanomaterials in two ways. Okay, in two ways, top down approach and bottom up approach. So these are the examples for top down approach and these are the examples for bottom up approach. Okay, right. So we will see how this nanotechnology plays a major role or new applications, or how this nanotechnology brings new flavor. Okay, new flavor to the existing applications. Okay, the existing applications in medicine, in electronics. Okay, we will see so the major advancements in different fields due to this nanotechnology. Okay, so the first one is we will see medicine. Right, medicine, I already told you. So nanotechnology plays a major role in drug delivery system. Okay, drug delivery system. drug delivery system. Right. See, nano carriers, liposomes or missiles, can transport therapeutic agents directly to infected or cancerous cells, enhancing efficiency and minimizing side effects. So usually, so whenever we have a problem, we take medicine, but it can travel to some unnecessary places also. The medicine can go to unnecessary areas also. So that is some of the side effects, so with our uh, existing medicine taking process. Okay, but it travels to unnecessary, the medicine travels to unnecessary places also. But by using this targeted drug delivery, we can take the we can take the medicine to exactly where it required. Okay, at the affected place. Okay, if you see this picture, see, so this medicine taken by nanoparticles to exactly at the affected areas. Okay, by using this technology, we can take the medicine to the affected areas. Okay, so right, another one is virus mimicking nanoparticles. So I already told you, biomimicking nanostructures imitate viral mechanisms to improve cellular uptake for vaccines and gene therapy. And also you can see breath-based diagnostics. Nanosensors detect volatile organic compounds VOC in human breath, enabling non-invasive diagnosis of diseases like cancer or infections. So by our breath, by analyzing or by diagnosing our breath also, so by using some nanosensors, so we can detect some of the diseases. We can detect some with breath analyzers. We can find many of the diseases. And also real-time disease monitoring. Nano-enabled biosensors allow continuous monitoring of biomarkers in body fluids for early stage disease detection. So usually we can, any disease, so if we detect it in very early stage, we can cure it in a better ways, right, in a better ways. So for these purposes, by using these many nanosensors, we can find many diseases very early stage. Okay, some personalized medicine, integration of nanomaterials with biosensing platforms supports customized therapeutic strategies based on individual patient profiles. So in medicine, for example, even in medical equipment, in MRIs, right, in CT scans, in radiology, for example, for cancer patients, excuse me, for cancer patients. So usually only the affected area, only if you give radiation to only the affected area, exactly specified how much percentage of power we should give. So in this process, nanotechnology plays a major role. Okay, so likewise nanotechnology brings many innovations in medical field. Okay, in medical field. Okay, right. The next one is nanomaterials in advanced electronics. Okay, nanomaterials in advanced electronics. See the three pictures. Observe this three pictures. So this is quantum dot LED. Okay, quantum dot LED. So this is a sensor. This is a transistor. Okay, microelectronics. Okay, nano electronics chip. We can call it as a chip, right? Yes, it is a chip. This is a flexible display device, right? Flexible display device. Okay, nanomaterials bring so many innovations in advanced electronics. So many innovations, right? So, for example, quantum dot displays. Nanocrystal quantum dots enable vibrant color reproduction and energy efficient displays in modern QLED TVs. Okay, so this is possible only through nanotechnology. This is possible only through nanotechnology and flexible electronics. So Nanoscale materials, for example, if you take one-dimensional nanomaterials, so usually there are um, 3 to 4 different types of nanomaterials, zero-dimensional nanomaterials, okay, one-dimensional, two-dimensional, three-dimensional nanomaterials. So every nanomaterial has its own advantages, different applications, okay. So for example, if you take a flexible electronics, so we use graphene and conducting polymers, so they provide highly conducting high electrical conductivity, okay. So nanoscale materials such as graphene conductive polymers are used in bendable rollable displays for next generation mobile devices and wearable electron. For example, if you you can have a wristwatch, flexible watch, okay, flexible watch, and flexible rollable television displays, okay. So for to achieve these flexible electronics, you need nanomaterials, right? So one dimensional materials, two dimensional materials, okay. And also see this one, nanoelectronics for miniaturization. Nanotechnology enables the design of ultra small high performance transistors for faster, more efficient integrated circuits, okay. See, there is a law that is, I think it is Moore's law. So you need more transistors, you need more circuits, but how can we integrate more circuits? By decreasing the size, okay, by decreasing the size. How can we achieve that? By utilizing nanotechnology, by making nanomaterials. By making nanomaterials, you can scale down this chip size, okay. You can make nano chips, you can make nano chips by utilizing, by preparing and utilizing these nano chips only, we can achieve this nano efficient nano electronics, okay, efficient nano electronics. Nowadays we are using AI, right? Artificial intelligence. To run artificial intelligence, you need high efficient devices, right? High efficient devices, right? So this Nvidia company making these devices, so which are essential to run artificial intelligence, to run GPTs, right? To run GPTs, so it needs high very fast responsive devices, right? So these are all possible only through making highly advanced nanomaterials, okay. And also improved semiconductor devices. Nanomaterials enhance charge mobility and thermal management in electronic chips, supporting, yeah, AI and quantum computing. We need devices, we need this kind of devices to support AI, quantum computing. We need a fast responsive systems, okay. And energy efficient optoelectronics. Nanostructured materials improve LED and laser performance, reducing power consumption in smart gadgets. Right. So we need highly efficient, power efficient devices. Okay, power efficient devices. So all there is lot of electronics and electronic devices in today's world, so we are using, so those are all the byproducts of nanotechnology only, right? So that's why nanomaterials having a big role in today's advanced electronics, okay, in today's advanced electronics. Right. Nanomaterials in energy applications. Nanomaterials in energy applications. So we are all very familiar with electric vehicles, right? We are very familiar with electric vehicles. So these electric vehicles, how do we charge? We need a battery, right? We need a big batteries, right? So nowadays we are using lithium ion batteries, right? Lithium ion batteries. And you can see this three pictures. It is electric vehicle. These are solar cells, okay? Wind energy, okay? So these are battery materials, okay? This is lithium ion battery, okay? Lithium ion battery, okay? Right? Next generation lithium ion batteries. So how do we make batteries to store more energy? For example, previously we use primary batteries, okay. So that means it cannot be rechargeable, for example. So if you see a wall clock battery, it is not a rechargeable battery initially, Okay, so but we need rechargeable batteries, so that means we need to charge, and we will use, and then it will, that means it is discharged, then again we need to recharge. So we need rechargeable batteries, not only rechargeable batteries, and the battery should, uh, it has a capacity, it should have more capacity, and should have more power to deliver. Okay, so for these purposes we need new advanced batteries, so that is lithium ion batteries. For example, nanocomposites, something like tin oxide and carbon nanotubes, enhance electrode conductivity. So here I take, there is a lot more materials to make lithium ion batteries anodes. So here we can take SnO2 and carbon graphite. Okay, so single walled carbon nanotubes. So we'll make some other material. So these nanocomposites, what they will do, it can store more energy, it can store more energy, it will deliver high power. Okay, so how it is possible to make highly efficient electric vehicles? So battery is the heart, right? Battery is the main component in electric vehicles. Battery is the main component in electric vehicles. So in that battery, in that rechargeable battery, we need nanomaterials, we need nanomaterials, we need highly advanced nanomaterials, we need nanomaterials which should store more energy, which should be more efficient, which should be more stable, which should be chemically more stable, right? So it should have many properties. Okay, it should have many properties, it should have many properties. How can we achieve? By by making different nanomaterials. So see, every material has its own advantages, different properties. Okay, so we need to select materials which are suitable to make a battery, right? Because it should have more surface area, so that it can provide highly active surface, and it should not be more volume expandable materials. Okay, so whenever we charge, so if you see some of the batteries, so after charging, after utilizing many days, the battery will bulge, the battery will expand. Once the battery will expand, what will happen? It will explode. It should not happen. So we need to make a material in such a way that it should not have more volume expansion. It should control, right? And also it should have good conductivity. It should have good conductivity. It should be chemically stable, right? So we need to, so a good battery, an ideal electric vehicle battery, the material which we are using, it should have some properties for a better battery. So we need to choose the material. We need to prepare the materials, right? We need to prepare the materials. So that's why nanomaterials are very, very crucial to make a battery for electric vehicles. Okay. So in energy applications, so be not only electric vehicle battery. For example, if you want to make efficient solar cell, so it should absorb more energy from sunlight. It should convert more light into electricity, right? So that means the properties will change. The nanomaterial required for solar cell, the nanomaterial required to make a battery is very different, because it demands some other properties. That's why suitability or selecting nanomaterials for different applications is very different, right? So we'll see electric vehicles. Nanostructured materials reduce weight and improve energy density, enabling faster charging and longer driving ranges. So one of the requirement is it should fast charge. We should charge the battery very fast, but we should, the discharge time should be high, right? So and also the battery should not be more weight. For example, if some material have more weight, some materials have lightweight. So we need lightweight materials which can store more energy. which should have more energy, right? So it's not very simple to make a rechargeable battery to use for electric vehicles. It demands different properties. It demands so many properties, right? So it is one of the properties. See here, it should reduce weight, it should be less weight, and it should improve energy density, enabling faster charging and longer driving ranges. So we will charge, discharge, charge, discharge, charge, discharge. So it should have more stable. It should be more stable. If you know, for example, if you utilize 1 year, so our mobile battery, what will happen? What will happen to our mobile battery? The efficiency will decrease. In initial days, if you full charge, it will sustain for 1 day. But after utilizing 1 year or 2 years, then the battery life will come down to half, 50%, 60%, right? So we need more efficient batteries, more efficient batteries, right? More efficient batteries. And also coming to solar cells, what else we required? We required energy harvesting and storage. Nanomaterials enable efficient conversion. Efficient conversion means, so it should convert 15% of sunlight, 20% of sunlight, 25% of sunlight. So the efficiency of conversion should be more. If it convert more sunlight into electricity, it is more advantageous, right? More advantageous, right? So, and also storage in renewable energy systems like solar cells and supercapacitors, solar cells, batteries, right? So these are all energy related applications. In all these applications, we are using nanomaterials. We are preparing different kinds of nanomaterials, right? So sustainable energy systems. Integration of nanotechnology in wind and solar energy infrastructure boost efficiency and support smart green cities. For example, if you take these windmill, if you make this wings, right, with lightweight at very strong, so that it can rotate very fast, even wind is small, right? If it is more weight, it is very hard to rotate, it is very hard to revolve, right? But if you make with new innovative materials which provides lightweight and very high strength, then it is very advantageous, right? Then it is very useful. So it will rotate more, we can create more electricity. So nanomaterials plays a major role in energy applications. Okay, techniques such as ultrasonification, filtration enables. So this is related to preparation of nanomaterials. Okay, preparation of nanomaterials. Okay, so nanomaterials provides very useful applications. Okay, useful applications. So integrating nanotechnology nowadays is very essential in all the technologies, be it medicine, electronics, and energy applications. Okay, so coming to environmental applications. Okay, coming to environmental applications, nanotechnology have tremendous huge number of applications related to environment. Okay, environment. See, you can see here environmental applications: tap water, water pollution, air pollution, irrigation, agriculture, soil. So we can treat water pollution with nanomaterials. We can treat air pollution with nanomaterials. We can reduce air pollution. We can we can reduce water pollution, and we can utilize in irrigation, that is in agriculture, in soil. So there are a lot of environmental applications. Okay, so by using photocatalysis, we can treat water and we can treat air. We can decrease the pollution. We can decrease the pollution. See here, nano sensors detect environmental contaminants in tap water, polluted water, air, soil, and agriculture systems. We can use nanosensors, biosensors, so that we can test, we can identify how much pollution it has. So in tap water, water pollution, air pollution, VOCs, volatile organic compounds. Okay, so nowadays we are facing so much in this pollution, water pollution, air pollution, right? Air pollution. So nowadays we are using water, we are treating water, our drinking water. We are using many machines, hmm, to treat water. So we are using, there are some nano filters, okay, some nanomaterials. By using some technologies, we can treat water pollution and air pollution and all this. So these are the process. Nano photocatalysis. We can use nano materials like basic materials, zinc oxide, titanium dioxide. So these are all basic materials we can use to treat air and water. Okay, you can see here, nano photocatalysts remove wide range of pollutants, including organic dyes, heavy metals, pharmaceuticals, and pesticides by using advanced redox reactions. You can see here, advanced redox reactions. By using this, we can reduce pollutions. Okay, mechanistic versatility. These catalysts operate through adsorption, ion exchange, redox reactions, ensuring comprehensive detoxification. Okay, there are different approaches to treat these pollutants. Okay, particularly water pollution and air pollution. Okay, and also, for example, nowadays we are using air purifiers. Okay, in closed rooms, air pollu air purifiers. So we have already water purifiers. Nowadays air purifiers also we are utilizing it, required in hospitals or in offices, where many people working in a small space where there is no proper ventilation. We need air purifiers also. Okay, air purifiers. So for example, if you consider some metro cities like Delhi, Mumbai, Hyderabad, Kolkata. So air is heavily polluted, right? Air is heavily polluted. There we must have air purifiers. We must have air purifiers. How can we achieve this? By using nanomaterials, by utilizing nanotechnology, we can purify air up to some extent, not fully, up to some extent. We can purify. That's why nanotechnology is essential. Okay, and also nanotechnology in everyday life. Okay, nanotechnology in everyday. See this slide. See this slide. Have you found anything? Have you related to your daily life? Yes, right? So we will use sunscreen lotions, right? Why do we need sunscreen lotions? So now right now this is summer season, right? So when if you go out, your skin will burn because of this heavy UV rays. Okay, heavy UV rays. So how can we protect our skin? By utilizing some sunscreens. Okay, by utilizing sunscreens, right? So here also nanotechnology comes into picture. For example, all these sunscreen lotions, sunscreen creams are made up of nanomaterials. What they will do? So if you apply these cream, or you can simply call this nanomaterial uh, creams, if you apply on a skin, so it will protect your skin. It will reflect the UV rays. It will reflect the UV rays so that our skin may not damage that much extent. Okay, so see some of the sunscreens. Zinc oxide in nanoscreen. These zinc oxide nanoparticles block UVA, UVB rays, offering better UV protection without white residue. Okay, so there are many materials. So zinc oxide is zinc oxide, TiO2. These are the basic nanoparticles utilizing in this application. So it will protect from UV rays. It will give you enhanced UV protection. So this diagram shows zinc oxide layer on skin reflecting harmful UV light for safety. So I already told you. So these cricketers utilize come. We will see cricketers with sunscreen lotions on ground, right? So what? Why they are utilizing? To protect from sunlight, right? From this harmful UV rays. Okay, and also you can see this picture. What is this picture? In our daily life, you can see. So energy saving windows. Energy saving windows. Usually we will coat with some shaded, black shaded coating, right? So what will they? These glass doors protect from UV rays, so that the indoor will be little bit cooler, right? Because it blocked the UV rays. Okay, and also we will use our glasses also with blue light. Okay, blue light filter, UV light filter. What they will do? It will reflect UV rays. So if you see direct, it will the UV rays pass into our eyes, right? But if you use UV filter glasses, what will happen? It will block the UV rays. It will protect our eyes. Okay, right. So in this way also, nanotechnology is very useful in our daily life. Okay, in our daily life. So zinc oxide in sunscreens, it will protect from UV rays, energy saving windows. So you can see many applications in our daily life, this nanotechnology. Okay, particularly in blocking UV rays, and also self-efficient glasses. For example, if you coat nanomaterial with outside surfaces, what will happen? So the dust automatically slide down. Okay, self-cleaning glasses, right? Self-cleaning glasses. So future of nanotechnology. So you can see this one. It's very interesting. Nanobots. Nanobots in medicine. Okay, nanobots in medicine. Futuristic nanobots could perform precise medical repairs, targeting diseases at the cellular level, at atomic level. So these small bots, nanobots, can carry the medicine to exact places, so that the side effects will minimize. Side effects will minimize, because we are taking the medicine to the affected area, so that the drug will not reach to unwanted places, so that the side effects will decrease. So that's why it's very futuristic concept. So these nanobots, and also AI in nanotechnology. Okay, AI in nanotechnology. So AI accelerates nanomaterial discovery, optimizing properties for specific applications. Okay, for specific applications. See this. If you see this picture, have you reminded anything that happened in previous days? I think in Mark Zuckerberg, a Facebook founder. So he discussed about some technology. So by using some glasses, so we can communicate with glasses. We can communicate with glasses, just like a assistant. Okay, just like assistant, smart assistant. And smart materials, nanostructures enable materials that adapt to conditions, enhancing functionality in industries. Okay, we will use different smart materials which provides various properties, diverse applications, right? We will, and also self-repairing materials. For example, if our skin has some cut, okay, with knife cut. So what will happen? So if you apply just a material, just like a sunscreen we applied, right, on our skin. So if you applied skin, so it should self repairing, right? Self repairing. Right? So this is also happening. It may happen soon. Nanotechnology creates materials that heal themselves, extending durability and reducing waste. Okay, and also visionary applications. I already told you. From enhanced sensors to revolutionary healthcare, nanotechnology promises transformative innovation. So, this nanotechnology brings so many innovations, so many applications beyond our expectation, beyond our imagination. So many advantages we are witnessing in our daily life in various fields due to this nanotechnology. So that's why nanotechnology is our future. Okay, right. So in this lecture, so what else we found? What else we observed? See this slide, see this slide, and see all the key takeaways from this lecture. Go through this slide once. What else we have discussed in this lecture series? Lecture in this 1.5 lecture. So we have discussed from very basic things to how this technology evolved, how this technology is bring many new things in different applications, right? So initially we discussed about nanoscale, right? What is nanoscale? What is 1 nanometer? 1 nanometer is equal to 10 to the power minus 9 meters, right? How can we define nanoscale? How can we define nanoscale? How can we define a material is under nanoscale? If any one of the dimension falls below 100 nanometers, then we can say it is a nanomaterial, right? And what is the importance of nanoscale? What will happen when a material falls under nanoscale from microscale? At macro level, the same properties is different. Mechanical properties, physical properties, chemical properties at macro level. The same properties at nano level will change, definitely change. And this change bring new things to that material, new capabilities to that material, right? So this is the advantage when you scale down, when you bring down that material from macro level to nano level, the properties, the new properties bring new innovations, new technologies. Okay, so that's why it is very crucial to understand the science at nano level. The science at nano level. Okay, so what are the main reasons for this change? One is, what is the first one? Surface area to volume ratio. What will happen when macro level to nano level? Surface area to volume ratio will increase or decrease? Will increase, right? So macro to nano, surface area will increase from macro size to nano size. Okay, so what type of properties will change? Most of the properties will change, right? Because of the high surface area. Because of high surface area, nanomaterials, for example, material properties like optical properties, electrical properties, mechanical properties, magnetic properties, all the properties will change at nanoscale of the same material from its macro scale. So that is the advantage. That is the advantage of the nanoscale materials. Okay, so where do we find these applications? In most of the fields. For example, we already discussed in medicine, just like drug delivery, in electronics, like flexible electronics, right? In solar cells, in energy technologies, in batteries, in supercapacitors. How do we bring the new change, new things to battery? By making new materials which provide novel properties like high surface area, right? With chemically stable materials. So all these bring How this is happening? Only because the material is at nano level, only at nanoscale, right? Only at nanoscale. So is it, do we find this technology in nature? Yes, it is. What are the examples? Lotus leaf, right? Lotus leaf, it is hydrophobic, hydrophobic, so that the water can easily slide down. So by with that inspiration, we can make nanomaterials so that we can make glass windows which can self clean. No need to water, no need to clean every day. The dust particles incident or deposited on the surface will automatically clean, right? So these are all the advantages, right? So in any field, if you take any field, electronics, medicine, in space applications, in defense applications, in medical application, in medical equipment. So wherever you find anything, in anything you can find nanotechnology, right? Nanotechnology. So, so we can find many futuristic applications this with this nanotechnology. Okay, so these are all the takeaways, right? These are all the takeaways. So we will go once through this slide. Okay, see this one. This is the basic measurement. If you go up, the scale increased. If you go down, decreases. So where is our subject? Where is our focused area? This is one nanometer. See, now you can understand what happens when the scale goes down, right? Now you can understand. So definition definition of nanoscale, 1 billionth of nanometer. I think you can now compare our hair, how much is bigger if you compare with the nanoscale. Okay, nanoscale. So see this one, see this statement: materials exhibit unique physical and chemical properties. Okay, right? So what are the main reasons? Quantum mechanical effects, right? Quantum mechanical effects. So this is atomic level, right? Atomic level, nano level, micro level, macro level. Now you can understand how the properties will change when it goes down from macro level to micro level, right? Macro level to micro to nano to atomic level. So see this one. What are the examples here? Nanomaterials. You can find nanotubes, carbon nanotube, graphene sheet, gold nanoparticles. So these are all nanoparticles, right? These are all nanoparticles. Examples for nanostructures. Examples for nanostructures: nanoparticles, nanotubes, nanoflowers, nanocubes, nanotetrapods. So a lot of, there are so many morphologies, so many shapes of nanostructures available. Okay, see, unique properties, because what is the reason? Increased surface area to volume ratio. This is the main reason. Increased surface area to volume ratio. And second one, quantum effects, quantum confinement. Okay, size dependent properties. See, we have discussed it, right? Mechanical properties will change, electrical properties will change, magnetic properties will change, chemical properties will change, right? We can make lightweight materials with high toughness, high strength. We can make more electrically conductive materials for highly flexible electronics, right? We can make different magnetic properties, and if you, as you increase surface area, so we can make it more chemically reactive, right? So that we can store more energy in batteries, right? So very essential, it is very essential to study nanoscale, right? Nanoscale. So he's the father of nanotechnology. What is the famous statement? There is plenty of room at the bottom. There is plenty of room at the bottom. Now you can understand the, after this 1.5 lecture, you can understand the weight or the meaning, the importance, the essence of essence of this statement. There is plenty of room at the bottom. Still today, even after 10 years, even after down the line, how many years, there is so much to explore. Where? At the bottom, okay, at the surface, at the surfaces of material, at the surfaces of objects. Okay, so this is the basic, this is the first device, right? This is STM, scanning tunneling microscope. What are these? These are all carbon allotropes. Okay, these are all carbon allotropes, buckybars. Okay, see, so once, now you understood the concept, the ideology. Okay, so when you decrease the size, what happened? If you decrease the size, surface area will increase, surface area will increase. Okay, see this, reducing particle size increases total surface area. Okay, total surface area. So how can we make this? Yes, so these are the nature, nanotechnology in nature, right? So no man prepared these lizards with this technology, right? So it is there, it was there, right? So this is hydrophobic surface in nature. So that's why we have to observe nature deeply, right? We should inspire from nature. So these are all the tools for nanoscale, for nanotechnology. Okay, these are all the methods, or these are all the techniques, these are all the devices. Okay, so this is top-down approach, bottom-up approach, examples for top-down approach, examples for bottom-up approach. Okay, applications in medicine, applications in electronics. Okay, so nanomaterials in advanced electronics. So now whenever you go to electronics shop, you will immediately see what are the display technologies right now, right? You can observe quantum technology, you can observe quantum dot LEDs. So these are the most advanced display technology right now. Okay, flexible electronics. So I think we are witnessing foldable phone, right? Samsung Fold, right? Samsung Fold. Huawei, I think it has three fold phones, right? Three ways, one, two, three times we can fold. Okay, three fold. So that is the advantage of flexible electronics, right? That is the advantage of flexible electronics. Similarly, in energy, so now you will understand the importance of EV battery. So now in EV vehicle, how important is battery? how do how can we make a battery? What is the technology in batteries? What kind of properties a battery should have? So now you are aware of this electric vehicle batteries. Similarly, solar cells. Now we must utilize sun, right? We must utilize sun. It is free, it is abundant. So now every house should have solar cells, right? So nowadays government also incentivizing, right? So if you have a solar heater, you don't need to utilize electricity. You can get hot water every day, right? Solar water heater. So if you have efficient solar panels, so it will convert more sunlight into energy, right? So there the nanotechnology plays a major role, right? So see, these are all the examples for energy applications, and also to treat water pollutants, air pollution. So we are suffering, right, with this air pollution and water pollution. We can use nano purifiers, air purifiers. Hmm? So a lot of applications. So there is so much scope to study nanotechnology. There is so much scope to study nanotechnology in every field. So it's not an individual subject, right? So it is a multidisciplinary, it is interdisciplinary. So you can find in every stream of subject, every stream of branch, right? In electrical, mechanical, civil engineering, right? So even in computer science, even in AI, in quantum computing, right? So quantum computing is the future. Quantum computing is the future in the artificial intelligence. So wherever you find, so wherever, whatever the field you think you should utilize, you will find the nanotechnology application. See, in everyday lives, from sunscreen lotion to self cleaning glasses, UV protecting glasses. So see this, our future in nanotechnology. We can make smart materials. We can make this highly interactive interface with through lenses also, through lenses. So there is a lot more. Okay, so I hope you will understand the basic related to nanoscale, right? So thank you. uh, if you like this content, share with your friends and like this video. Comment, share your comments. If you have any doubts, you can post your comments. I will try to explain to your comment. Okay, please like, share this video with your friends. See you next time. Next we will come up with another concept in nanotechnology, that is quantum confinement. Okay, quantum confinement. Thank you so much. Thank you.